Good afternoon, ladies and gentlemen. Many thanks for having me. My name is Valentin Gurknecht, and I'm the co-founder and co-CEO of the company Neustark. And what we do at Neustark is developing solutions to permanently capture and store CO2 in demolished concrete. And in the next 15 to 20 minutes, I want to show you why we're doing that. I'd like to show you why, especially in this context, it's important to talk about value chains and solutions and not just technology. And last but not least, I want to show you what you can do right now to basically become part of this movement. So let me start with why, and I'm going to touch on a couple of points which Patricia brilliantly introduced and give them maybe kind of a different twist. So basically the world through the Paris Agreement has agreed to reach net zero emissions by 2050. More and more countries and organizations are making those commitments more binding, and most importantly, in the context of this conference, the European Union has also made this a binding goal. So we're talking about climate neutrality, and more specifically, we're talking about net zero emissions. And I'd just like to elaborate a bit on our understanding of that term, because I think there's a lot of confusion around it. So what do net zero emissions actually mean? Well, you've heard it. First of all, we have to avoid emissions wherever possible. That's key to reach our climate goals. The term net zero, although acknowledges that there are going to be some unavoidable emissions where we do not see how to completely get rid, for example, of fossil fuels by 2050. And net zero simply acknowledges that and says that each and every ton which is still going to be emitted will have to be rebalanced by another ton of CO2 removed from the atmosphere and permanently stored. And by talking about non-avoidable emissions, we're really talking about hard to mitigate sectors such as aviation or agriculture, where we're not only talking about CO2, but also of other greenhouse gases such as methane, of course. So what does that mean on a European perspective? If we have a look at the climate scenarios of the European Commission, we can conclude that maybe around about 7% of the EU's emissions are considered such unavoidable emissions. And that would mean that by 2050, we would need to capture and store alone in the EU around 300 million tons of CO2 from the atmosphere each and every year through so-called negative emissions technologies or carbon dioxide removals. And developing such a carbon dioxide removal value chain is exactly what we do at Neustark. And we do so specifically in the waste stream of demolished concrete. And that might come surprising for you, but demolished concrete is actually not only Europe's, but the world's largest waste stream as of today. That can be worrying, but it can be also considered as good news, because this largest waste stream chemically holds the potential to permanently store CO2 and basically turn the CO2 into stone. So if you contact CO2 with demolished concrete, the CO2 will eventually turn into calcium carbonate. So we petrify the CO2, or there's potential to petrify CO2 in this huge waste stream. And we think that's great news. And we think that should be developed, and that's what we're doing. And here is how we're tackling this challenge. So clearly we're talking about a value chain, a solution, and not just a technology. So first of all, if we want to get this implemented, we have to understand how demolished concrete is processed in the industry as of today. So typically, the demolished concrete is collected at a deconstruction site. It's then brought to concrete recycling sites where the material is crushed and sieved into a recycled concrete aggregate, which is as of today already sometimes landfilled, but in Europe mostly reused as a road-based construction material or even as a replacement for sand and gravel for the production of fresh concrete. So this is today's existing industry process. Demolished concrete is collected at concrete recycling sites and then crushed into a recycled concrete aggregate, as you see it on this slide. So what's new with Neustark is that we, as Neustark, start in more and more sites capturing so-called biogenic CO2, so CO2 which stems from the combustion or fermentation of biomass. We capture that CO2, we liquefy it and bring it to the concrete recycling sites so that there the gas can be contacted with the demolished and crushed concrete. And there it's being turned basically into stone. So that has one benefit of improving the material properties of this recycled concrete aggregate. And the second benefit is, of course, that we turn CO2 into stone and that we can measure exactly how much CO2 we turn into stone. We have double measurements for this. And that we can be sure that this CO2 will be removed and stored for thousands, if not millions of years as we turn it into limestone. And that material is going to be stable as many of the natural limestone formations, which we all know, such as parts even of the Alps. So we've developed a methodology under the gold standard to basically credit those CO2 removals. This allows us to make this transparent and also to market then those CO2 removal certificates to any country, organization, or even individual who has set for himself a climate goal. We can then help to achieve that. So much for the theory. I think the exciting part is that we're not just thinking about this. We have been thinking about this since 2017 when research started at ETH Zurich around this concept. But since last year, we're actually doing this. So what you see here is the biogas plant of the Bern wastewater treatment plant, where biomass, so for example, the trees, which you see in the background, are fermented as of today. Then the biogas is produced. Biogas is a mixture between methane and CO2. So what's happening is that this CO2 is scrubbed from the biogas. And as of today, or until last year, it was being released through this very chimney here on the top right. So what's new now with Neustark, and that's to be replicated with many biogas units in Europe and across the globe, is that we capture the CO2 so it doesn't get re-released to the atmosphere. We liquefy it, meaning that we pressurize it into 20 bars and we cool it down to -20 degrees so that it can be transported in those containers, which you see here, to the concrete recycling site where our technology is then located. So here you see a mobile Neustark unit consisting of the CO2 tank, then the process control unit behind the tree, and in the foreground, 2 of up to 6 reactors in which the concrete granules are basically contacted with the CO2. So the process, which can really be implemented by pretty much any concrete recycler in Europe, looks as follows. So first of all, the concrete rubble is filled to the reactors. Then the reactors are placed on the ground again at our plant. The CO2 gas system is connected, and we then start the process so that within 1 to 2 hours, in the 20 tons of material inside a container, we can store about 200 kilograms of CO2. We can be sure about the storage because we can measure the full process with 2 approaches. So first of all, we simply measure how the mass of the whole container takes up as CO2 is being stored. And then we can also calculate the material balance between the CO2 flowing in the container and flowing out of the container. And two measurement systems consistently give us really exactly the same result. So we have a maximum level of transparency here, which is a key issue in the field of CO2 removal, especially with our process, as like from the sheer eye, you couldn't tell if the concrete was carbonated or not. So after the process, the material can either be directly reused to build roads, to build fresh concrete, or it can be stored on piles for days, weeks, months, or even years. Anyway, the CO2 is not going to be released from the material as we've turned it into limestone. And we really went all the way also to see how then the recycled concrete treated with our process acts when it's being reused. So we did so for the case of recycled concrete, not only in the lab, but really all the way to commercial construction sites. So what you see here is really a Neustart recycled CO2 sequestering concrete being applied for a construction project of the city of Bern. It's a school which is built this spring. And you can really tell that the concrete then can be implemented 100% to today's standard practices on the construction site. So the full solution is really ready to be deployed. We don't have to wait for changes in the industry upstream or downstream. And we think that's key as we need to start to deploy those technologies really now in order to reach the necessary scale a couple of decades from now when we should reach those net zero emissions. So we're turning the CO2 into limestone, and we can observe that under the microscope. So on the left side, you see a recycled concrete particle under the microscope before our process. And on the right side, you can see really how those limestone crystals are formed on the surface and in the pores of this recycled concrete aggregate. So the reaction basically happens with cement, which is still present in this old concrete. And this change in surface and reduction of porosity of the material improves the material properties of the recycled concrete aggregate. And here you see that for the reuse case of production of a recycled concrete. So we have here two concrete mixes, left a reference and right the exact same recipe, which is using the treated recycled aggregate. And you can see how here we were able to increase the compressive strength of the concrete by more than 20%, meaning that in the second step, then the same quality of concrete, the same compressive strength could be achieved by using less cement. And that helps the economics of the process, of course, because cement is expensive, but cement is also CO2 intensive. So we have the potential to not only store CO2 through this approach, but also to avoid CO2 as less cement is used for the production of concrete. So again, talking about solutions and not just technologies, we of course have to have a close look of the full value chain of our approach and see if we can really have a net positive effect on the climate. So if we look at this full value chain, it starts with liquefying the CO2 at the biogas plant. We then have to transport the CO2 to the concrete recycler. There we have to evaporate the CO2, and then we have the full Neustart process actually happening at the concrete site. And only after that, we are going to store CO2. So here you can see that all of those process steps, there are to be respected and to be deducted to come to a net removal of CO2. But you can also see clearly that we have a positive effect in Switzerland. So CO2 liquefaction is the main driver for our own process emissions. We need around 250 kilowatt hours of electricity to liquefy the CO2. In Switzerland, we have a low CO2 intensity in the electricity mix. But even if we operated in Germany, where we still have much more coal-fired power, we would have a clearly positive effect. And I think this slide just reconfirms the point that we really need to develop full solutions, full value chains, and not just technologies in this space. Well, CO2 removal in general, but in our case especially. So if we just invented a way to store CO2 in concrete, the CO2 will still not get to the concrete recycler. Nobody would know how to reuse the material afterwards, so nothing would happen. So speeding up those developments, it's really important to own the full process A to Z, so that it's actually implemented, and so that it's implemented in the right way, leading to an optimal net result, as we see here. So what's the potential impact we could have with such a solution? For that, we need to have a look at how much CO2 is demolished today and in the future. And I told you that already today, demolished concrete is the largest waste stream in Europe, and it can be expected that this waste stream will double up decade after decade in the years to come, and that's quite easy to predict, as we simply have to look back 60 to 80 years and see how much concrete was produced back then, and those buildings reach basically end of life today. So Europe's largest waste stream is doubling up decade after decade. Again, this could be somewhat worrying, but I think it doesn't have to be, because the material first can be reused, and it holds the potential again to store CO2. And if we look into 2050, we'd be talking about the theoretical potential of 200 million tons of CO2 storage per year. So that's not the 300 million tons roundabout, which we're going to need, and we're not going to achieve the full theoretical potential here. So we are clearly not a silver bullet. We're going to need a combination of approaches. We are most importantly also going to need solutions like direct air capture, which you'll hear about later, and we'll need different storage solutions, also geological storage solutions, as the one being deployed right now in the North Sea. And we think that those solutions really should complement each other in an optimal way. You can consider CO2 storage in demolished concrete as a low-hanging fruit. You can do that whenever possible, and when you can't do that anymore, you can ship the CO2 for a longer distance and store it underground in the North Sea, for example. And another nice thing about this approach is that it's rather decentralized, comparatively small scale, which means that it can be implemented right now, and that's being done right now. So here you see 4 different pictures of 4 different concrete recyclers in Switzerland testing our system, and that's just symbolic of dozens of recyclers in Switzerland, and also Germany as a next step, who tested our system and who really want to go for the full implementation. That can be done right now. So you might think, sounds nice, but so what? I'm not a concrete recycler, and maybe you're also not building a road or a house right now where you could use this recycled concrete aggregate. And I think there's still good news, because what we can really now offer in collaboration with those concrete recyclers is to remove and store CO2 as a service. So if you have for yourself or for your organization a CO2 reduction goal, and you'd like us to take care of your non-avoidable emissions and basically remove them from the atmosphere and store them, we are very welcome to get in touch, and you're invited to write to me personally. So thank you very much.
Valentin, good morning from Belfast. Marcin, well, you're here again. We spoke last month by Zoom. Congratulations on all that now Stark has achieved. And we understand, and perhaps we weren't aware of, the real cost of buildings is what damage is done to the environment as well. So we understand your argument about the true value of the the cement you're manufacturing and the difference it's making to climate change. How many employees does Now Stark have now?
So when we last talked, we were at 6, and now we are at 10. So
Good.
we are
And
still small, but quickly growing.
With that breakthrough technology, when will you be at 100, do you think?
We certainly should be there in 1 to 2 years if the current dynamic is going on, and if organizations and countries are really following up on all the pledges which are being done right now. So this is a key driver for this development.
Well, good luck on that, and we'll invite you to Belfast next year, and hopefully when you take the podium, you will have hit that number of 100 employees and perhaps someday 1,000. So good luck to Now Stark. Thank you for joining us from Switzerland this morning. Good luck.